In this video, we'll demonstrate XPath by running a number of queries over our bookstore data. Let's first take a look at the data. We've expanded it slightly over what we've been using in previous videos, but it continues to have pretty much the same structure. We have a number of books. Books have attributes ISBN, price, sometimes an edition. They have a title sub-element, authors with first name and last name. So we have our first course book and our complete book. And our complete book also has a remark, as you may recall. Then I've added a couple more books. I've added Hector and Jeff's Database Hints by Jeffrey Ullman and Hector Garcia Molina with a remark, an indispensable companion to your textbook. I've also added Jennifer's Economical Database Hints. For that, at a mere price of $25, you get some hints. And then finally, just to demonstrate certain expressions, I've inserted 3 magazines, 2 National Geographics and a Newsweek, and finally a magazine called Hector and Jeff's Database Hints. So with this data in mind, let's move to the queries. We'll start with simple queries and get more complicated as we proceed. In this window, we'll be putting our XPath expressions in the upper pane, then we'll execute the query and we'll see the results in the lower pane. The way XPath works, the first part of every expression specifies the document over which the XPath expression is to be evaluated. So we have the data that you saw in a document called bookstoreq.xml, and you'll see in each of our expressions that we begin by specifying that document and then move ahead to the rest of the XPath expression. Our first expression is a very simple path expression. It says navigate through the XML by going first to the root element called bookstore, then look at all the book sub-elements of bookstore, and finally all the title sub-elements. Let's run the query and we'll see our result below. So as we can see, our result here is actually written in XML. A little header appears, and then we see the 4 titles of books that are in our database. Now let's modify our path expression. Instead of only getting book titles, let's get book or magazine titles. We do that by extending our middle matching element here to use a sort of regular expression-like syntax, book or magazine, and we put it in parentheses. So now it says match any path in the data that starts at the bookstore element, follows either a book or magazine sub-element, and then finally a title sub-element. When we run the query, we see now that we get not only the titles of our books, but also the titles of our magazines. So far, we've mentioned element names explicitly in our path expressions, but as I mentioned in the introductory video, we can also use what's known as a wildcard symbol, the symbol star. Star says to match any element name. So now we're going to start again with bookstore, match any element below bookstore, and finally find title sub-elements below those any elements. Now it so happens that the only elements below bookstore are books and magazines, so when we run the query, we will get exactly the same result. So far we've been navigating with the single slash operator, which tells us to go one element at a time. We're at a particular element, and then we match sub-elements with the specific tag that we typed. There's also the double slash operator. As you recall from the introductory video, double slash says match myself or any descendants of myself to any length. So if I put a double slash title, what we'll be matching is any title element anywhere at all in the XML tree. We run the query, and again we get exactly the same result because we had already been getting all of the titles which were sub-elements of books or magazines. Now let's get something a little different. Let's put slash slash star. Now that's kind of a wild thing to put because it says I'm going to match any element in the entire tree, and furthermore it can be of any element type. Let's run the query and see what happens. What we get is a huge result. Let me just scroll down so you can see the result. In fact, what we're getting is every element at every level of the tree, including all of its sub-elements. So in fact, the first element in our result is our entire tree because it's our bookstore element, and we'll go all the way down to the end of the bookstore. The next element in our result is some children of the bookstore, so we get the book elements. And we're also going to get their children in the answer, and as we keep scrolling down, we'll see that we get every element of the entire database. So that's not a useful query, but it does demonstrate the constructs, the double slash matching any element in the tree, and the star matching any tag of any element. Now let's turn to attributes. Let's suppose we're interested in returning all the ISBN numbers in the database. So we'll go back to saying bookstore, book subelements, and then we'll get the attribute ISBN. So we type @ and ISBN. Let's run the query, and we get an error. It turns out that attributes cannot be what's called serialized in order to return them in an XML-looking result. So what we need to do actually is obtain the data from the attribute itself, and once we do that, we'll see that we're getting the answer that we desire. So we'll ask for the data of the attribute, run the query, and now we see we have all as ISBN numbers. Now the attribute data is just strings, so we're returning the ISBN numbers as a set of strings with blanks between them. So some of these are sort of peculiarities of how XPath works. Again, we were not able to return an attribute because it didn't know how to structure the result, but once we extracted the data from the attribute, it returned it as string values. So far, we've only seen path expressions with no conditions involved, so let's throw in a condition. Let's say that we're interested in returning books that cost less than $90. So what we're going to do here is navigate to the book, and then we're going to use the square bracket which says start evaluating a condition at the current point of the navigation. So the condition that I'm going to put is that the price of the book is less than $90. We'll run that query, and we'll see that we have three books, whose price is less than $90. Now here we return the book that satisfied the condition. What if what we actually want to return is the title of the books whose price is less than $90? What we can do is after evaluating this condition on the book, we can actually continue our navigation. So we just put /title here. It says find the books, only keep the ones that match the condition, and then continue navigating down to their titles and return that as the result of the query. We run the query and we see our result. Now another type of condition that we can put in square brackets is an existence condition instead of a comparison. If we put, for example, just the label remark inside our square brackets, that says that we should match books that have a remark. So putting an element name in square brackets is an existence condition on that sub-element existing. Once we've isolated the books that have a remark, we'll return the title of those books. We run the query, and we discover that 2 of our books have a remark. You can go back and check the data, and you'll see that's indeed the case. Let's get a little bit more complicated now. Let's get rid of this query and put in a whole new one. In this query, we're going to find the titles of books where the price is less than $90 and where Ullman is one of the authors. So now we have in our square brackets a longer condition. Price is less than $90, and there exists, and implicitly this is an exist, there exists a subpath from the book, author/author/last name, where the value of that is Ullman. If we satisfy both of those conditions, then we'll return the title of the book. So we run the query and we discover 2 books that are less than $90 where Ullman is one of the authors. Now let's expand this query by adding another condition. We want not only the last name of the author to be Ullman, but the first name to be Jeffrey. So now we're looking for books where Jeffrey Ullman is one of the authors, and the books are less than 90. So we run the query and we get the same result, not surprisingly, since Ullman is always paired with Jeffrey. But actually, this is not doing quite what we're expecting, and I'm going to explain why by demonstrating some changes. Let's say that we change our query to not look for Jeffrey Ullman as an author, but to look for Jeffrey Whittam. Hopefully we'll get no answers, but when we run the query, we see we still get a book, the first course in database systems. So the 2 authors of that book, if you look back at the data, are Jeffrey Ullman and Jennifer Whittam. So let's see why that book was returned in this query. The reason is, if we look closely at this condition, what we're saying is we're looking for books where the price is less than $90, and there exists an author's author last name path where the value is Whittam, and there exists an author's author first name path where the value is Jeffrey. Well, that in fact is true. We have one author whose last name is Whittam and another author whose first name is Jeffrey. Let's try to formulate the correct query now. So instead of matching the entire path to the last name and then the entire path to the first name separately through the author's subelements, what we want to do is we want to look at each author at a time, and within that author look at the last name and first name together. So to modify our query to do that, we're going to use a condition within the condition. Specifically, within the author/author, we'll look at the last name and the first name. This syntax error is temporary. Once we finish the query, everything will look good. So we put a second bracket there, and let me show again what I've done. I've said we're looking for books where the price is less than 90 and there exists an author/author sub-element where the last name is Whittam and the first name is Jeffrey. Hopefully we'll get an empty answer here. We execute the query, and indeed we do. Now our original goal was to have Jeffrey Ullman, so finally we'll change Jeffrey Ullman, run the query, and now we get the correct answer. Incidentally, it's a very common mistake when we have a condition to put a slash before the condition. If we did that, we'd get a syntax error. When we write the square bracket, it essentially acts like a slash. So when we reference a sub-element name within a square bracket, we're implicitly navigating to that sub-element. Next, we're going to try a similar query with a twist. We're going to try to find books where Ullman is an author and Whittam is not an author. So we navigate to books as usual, and we look for cases where there's an author's author, last name equals Ullman, and there's an author's author, last name not equal to Whittam. Now, you may already detect that this is not the correct query, but let's go ahead and run, and we see that we got 3 books, but we know the first 2 books, Whittam is an author. So, as you may have detected, this is not correct. What this asks for are books where there's an author whose last name is Ullman, and there's some author whose last name is not Whittam. Well, in fact, every book with Ullman as an author has some author whose last name is not Whittam. That would be Ullman. So even if I took away this condition and ran the query again, I'll get exactly the same result. Well, actually, I got a syntax error. Whoops, I forgot to erase the and, so let's get rid of that, run the query, and now we do, in fact, get the exact same result. So as a reminder, we were trying to find books where Ullman is an author and Whittam is not. In fact, we do not have constructs yet to write that query. A little later in the demo, we'll see how we can write it in a kind of tricky fashion. But for what we've seen so far with path expressions and conditions, we're unable to write that specific query. So far, we've seen 2 types of conditions in brackets. We saw comparisons and we saw existence constraints, where we checked to see whether a particular sub-element existed. As you might remember from the intro, we can also put numbers inside square brackets, and those numbers tell us to return the nth sub-element. Specifically, if we look at this query, we're using / to navigate directly to author's elements, and then we want to return the second author sub-element of each author's element. So we run the query, and we'll see, if we looked at our data, that Jennifer Whittam, Jeffrey Ullman, and Hector Garcia Molina each appear once as the second author of a book or a magazine. If we change this to 3, we'll be returning third authors only, and we can see only Jennifer Whittam is a third author. If we change this to 10, hopefully we'll get an empty result, and in fact we do. Now let's take a look at some built-in functions and predicates. In this query, we're going to find all books where there's a remark about the book that contains the word great. So we're going to navigate using / directly to book elements, and within the book element, we'll have a condition that invokes this built-in predicate contains, which I mentioned in the introductory video, which looks at 2 strings and checks whether the first string contains the second one. So if we have a book where there's a remark, which is a string, that contains the word great, then the book matches the condition and will return the title of the book. We run the query and we see that we have 1 book that has a remark containing the word great. Our next query does something kind of new. I like to call this query a SelfJoin, but that's probably because I'm a relationally biased person. But what it's actually doing is querying sort of 2 instances of our bookstore data at once and joining them together. So we'll see that our doc bookstore appears twice in this expression. Let me explain what this expression is doing. It's finding all magazines where there's a book that has the same title as the magazine. And here's how it does it. So our first path expression navigates 2 magazines, and then it extracts in the condition the title of the magazines. The magazine will match if the title equals some book title, and so to find the book titles, we need to go back to the top of the document. So we get a second instance of the document, and we find book titles. Now, when we have the equals here, this equals is implicitly existentially quantified. Follow that? Implicitly existentially quantified. That means that even though we're doing equals on what's effectively a set, the condition is satisfied if some element of the set is equal to the first title. Okay? There's a lot of implicit existential quantification going on in equality, in XPath, and in XQuery as well, as we'll see later on. In any case, let's run the query, and we will get back the fact that the magazine called Hector and Jeff's Database Hints has the same title as a book, and if you look back in the data, you'll see we do have a book of the same name. We saw one example of a built-in predicate contains. This example shows another built-in function, in this case, the name function, and it also shows our first example of a navigation axis. We're going to use the parent axis. What this query is going to find is all elements whose parent element tag is not bookstore or book. Of course, this is just for demonstration purposes. It's not really that useful of a query. But let me just walk through the construction of the query. So we're starting with our bookstore, and then we're using // which finds all elements. We saw // earlier when we ran the query. We saw that it matched every element in the book, in the database. Now, since we've already put in bookstore, we're not going to match the bookstore element itself, but we'll match every child of the bookstore element. So what the condition looks for is the tag of the parent of the current element, and it sees if it's bookstore or book. And we return the element if it's neither bookstore nor book as the parent tag. Here's how we find the parent tag. So name is a built-in function. Name operates on an element, and it returns the tag of that element. The element we want to look at is the parent of the current element, and the way we do that is with the parent navigation axis, which is parent : : Finally, the star is matching the tag of the parent. So here we say match any tag of the parent, extract the tag, and check if it's bookstore or book. So when we run the query, we'll see that we get back a lot of data, but all of them are elements in the database whose parent is not the bookstore or book. Here's another example of a navigation axis. In this case, we're using following sibling. Following sibling says that if we're at a specific point in the tree, we should match every sibling, so every other element at the same level that's later in the document, that follows the current sibling. So let's walk through this expression and see what we're doing. What this expression is looking for is all books and magazines that have a non-unique title. In other words, all books or magazines where some other book or magazine has the same title. So we navigate down to books or magazine elements. This is what we saw in one of our earlier path expressions, so we'll match any book or magazine element. And then we want to find one where the title is equal to some title of a later sibling. Now, our books and magazines are all at the same level in our data, so when we do following sibling, we're going to be matching all other books and magazines that appear after the current one. And again, this star says that we can match an element of any type. We could equivalently put book or magazine in here because we know they're all books or magazines, and we'll do that in a moment. But for now, let's just focus on running the query. So we execute the query and we find two answers. We find Hector and Jeff's Database Hints, which is a book because we had a magazine of the same title. And we find National Geographic, which is a magazine, because there's another magazine of the same title. So actually this query was somewhat incomplete, and that was our fault. The way we wrote the query, we said that we want to return book or magazine elements when a later one has the same title. So that doesn't actually return all of the ones with non-unique titles. It only returns the first instance of each one with a non-unique title. Let's modify the query to do the right thing. What we need to do is not only check whether the title equals the following sibling title of some book or magazine, but whether it might also equal a preceding one. So we add title equals the same construct using the preceding sibling axis, / title. Here we go. And now when we run the query, we see that we get Hector and Jeff's Database Hints and National Geographic, but we also get another instance of National Geographic and another instance of Hector and Jeff's Database Hints. So now we have the correct answer. We don't only get the first instance of duplicated titles, but we get both of them. Now, to show the use of this star, we were matching any book or magazine as the following sibling. What if all we were interested in is cases where there's a book that has the same title, but not a magazine? And we can do the same thing here. In that case, we shouldn't get National Geographic anymore. Let's run the query. And indeed, all we get, in fact, is Hector and Jeff's Database Hints as a magazine, because that was only the only instance where there was an actual book that had the same title, as opposed to matching books or magazines with the star. Don't take a look at this query yet. Let me explain what I'm doing before you try to untangle the syntax to do it. As I mentioned earlier, XPath revolves around implicit existential quantification. So when we are looking, for example, for an author whose name is Ullman, implicitly we will match the path if any author has the last name Ullman. And in general, most of XPath revolves around matching sets of values and then returning things if any element of that set matches the condition. What if we want to do universal quantification, in other words, for all? That turns out to be more complicated, but we can do it in a tricky fashion. So what we're going to do with this query is we're going to find books where every author's first name includes J. If we wrote it in the fashion that we might be tempted to, where we just say book author / author first name includes J, then we'll get books where some author's first name contains J. To get books where all authors' first name contains J is more difficult, and the way we're going to do it is, it's kind of a kludge, we're going to use the built-in function count. So here's what we're doing in this query. We're finding all books where the number of authors whose first name includes J is the same as the number of authors of the book without a condition. Okay? So specifically, under book, we count the number of matches of an author's author sub-element where the built-in function, the built-in predicate contains is true, where the first name contains J. And so we are counting the number of authors whose first name contains J, and we're setting that equal to the count of the first name sub-elements. We'll run the query, and we will find indeed that there are 2 books where all of the author's first name includes J. We can use a related trick to write the query we tried to write earlier but failed, to find books where Ullman is an author and Whittam is not an author. So with the implicit existential, what happened before is that we found books where there was an author whose name was Ullman, and then there was an author whose last name was not Whittam, and of course we still got everything back. What we want to find is books where there's a last name that's Ullman and where none of the authors have the last name of Whittam. That's effectively, again, a universal quantification, or for all. For all of the authors, their last name is not Whittam. Since we don't have a for all construct in XPath, we're again going to use the count trick. So in this query, we're looking for books where one of the authors' last name is Ullman, and the number of authors, using count again, the number of authors whose last name is Whittam is 0. So now we've expressed that query, we run it, and we get the correct answer. That concludes our demonstration of XPath. We've shown a large number of constructs, and we've written some fairly complicated queries. On the other hand, we certainly have not covered the entire XPath language. If you're interested, there are many online materials. We've also provided data, and we encourage you to experiment on your own.